Hello, welcome to chapter 6, jointly distributed random variables. Okay, we're going to have two parts as usual. Okay, so the first part, as you can tell from the chapter name itself, we're going to start to define what we mean by joint distribution. Okay, so we have seen marginal distribution about one random variable at a time. Now we're going to try to see how we can define what we mean by joint distribution for multiple variables at the same time. Okay, so to start with the definition, we're actually going to start with joint CDF. Okay, as you can see, especially if you recall what we're doing with the continuous random variable, right? Like in our definition itself, we started with CDF because that's what you can do about the integration, right? Like the part about talking about probability. And then once you have the CDF, the capital F, you can take the first order derivative to get the PDF. Okay, so this is following a similar logic that we're doing over here. We are starting with joint CDF, okay? And as you can see, regardless of whether it's discrete or continuous, you can always have this result. So the definition goes this way. We have a pair of random variables, x and y, okay? So the joint cumulative probability distribution function, so this is the CDF, okay? But then particularly joint CDF, okay, is defined by this, okay? So if you look at what we're doing, remember, now we start to add this subscript of capital letters to represent what random variable we're working with. In this case, because we're working with joint, so the notation goes this way, okay? So you can write x, comma, y, but both of them are capital letters just to represent that they're the random variable, okay? And of course, up here, we are also using capital F because that's the CDF, okay? So the definition goes this way, actually pretty intuitive, hopefully. Remember in the past, if you're working with one, say like fx, capital X here, right? What we do is the probability of the random variable small equal to small x, okay? So you do that for y. So here, as you can see, the definition goes that if we're working with a joint CDF, we are talking about the joint probability, right, of both events happening. Okay, so that's what we mean by joint. And if you try to think about this a little bit more graphically, okay, down here we're showing you a graph down here showing for x and y what we really mean by the joint CDF function. Okay, so x-axis represents x, y-axis represent y. So the small xy is, let's suppose, this point. Okay, so if I look at the definition, what we're doing, this joint CDF, right, is giving us the probability that the pair of x and y lies southwest of the point of small xy. Okay, so pretty much it goes all the way like this. Okay, so that's what we mean by the joint CDF. Okay, again, it is very similar to what we're doing back then with just one variable at a time, okay? But now we're talking about joint distribution, and the CDF is defined jointly by looking at probability of these two events at the same time, okay? So there are some important properties, okay, of joint CDFs, especially how we can do, let me just erase this clear, okay? How we can figure out, like say, if now I have the joint CDF of f and y, how can I get the marginal CDF of x from it? And how can I get the marginal of CDF of y? Okay, so this is what we mean by the property. Okay, so here, let's suppose we have fxy. Okay, so that's the joint CDF. Okay, and notice that we usually try to write in this way. So this is known. Okay, so what I'm trying to say is that if you do have the joint CDF, you actually will be able to get the marginal CDF of one of them. Okay, so for this case, if you want to get the marginal CDF of x, okay, it is equivalent to think about the joint of the x and y together, but then you can think of y as anything that can happen. Okay, so in this case, remember, when we're writing of CDF, this is representing random variable y is smaller than, small or equal to, or smaller than positive infinity. Okay, so this is saying that, well, if I want to know the marginal CDF of one of the random variables from their joint CDF, essentially what I'm doing is think about the joint CDF and then consider the other one as anything that can happen, right? So it's almost like ignoring the other one in this way, okay? And more formally, what you can do, as you can see here, is that if I go back to the definition of the marginal CDF, right, I have fx capital X, right? And then parenthesis small x, by definition, is probability of x is smaller or equal to x, okay? And then what we're doing is essentially, well, that's the same as the joint probability of x is still smaller, capital X is still smaller or equal to small x, but then y can be anything, okay? Y can be anything on the real line, and then that is equivalent of saying what we are showing the result up there, okay? So similarly, as you could imagine, you can do that for the marginal of y as well. Okay, so it works very similarly in the same way. So I would encourage you to walk through the logic in your after the video, so you can convince yourself that either way works in this manner. Okay, and lastly, if you're ever interested in finding about the joint probability of x is greater than small x and y is greater than small y, then you can use this result. Okay, so this result, if you see it, like just reading it, is very similar to the inclusion-exclusion probability property that we have seen before, okay? But just to bring you back into this general framework that we're talking about, okay? So remember, we're saying that the joint CDF, right, which is F, okay, so probability of x is smaller or equal to small x, y is smaller or equal to small y, right? That is anything on this that is to the southwest of this point, okay? Alrighty, so now if I look at what I'm trying to do, right? So I'm gonna use a different coloring here, okay? So if I want to get this joint probability, okay? And if I try to do it on the graph, what did I get? I have to have my x is greater than x, right? And then y is greater than y. So essentially, I think we're looking for this part. Okay, so this part, okay, so one more time, also just to remind you that when we're doing this kind of graphic work, we're saying that everything like the area, right, of the entire space that we're working with, the two-dimension space they're working with is 1, okay, because that's all possibility out there, so it's going to be probability 1, okay? So if you think about now, the goal is to try to get this, okay? So that is equivalent of doing, so you can see, let me use another color here, okay? So fx, okay? fx for the notation that for this graph, fx, I think, let me use my coloring hopefully correctly over here. Okay, so it's going to be everything on the x-axis that's smaller equal to the small x, right? So that will be everything over here. Okay, and then lastly, let me see if I have, okay, I do have one more color that I can do. So everything smaller or like everything about this fy is going to be everything below this part. Okay, so anyway, so once you work it out, I think you will be able to convince yourself that this expression works just fine, okay? And I would just say that this in some way is very similar to the inclusion-exclusion probability result that we saw before, because when you have two events, right, when you have any kind of intersection between them, if you want to know the union of the two, right, don't forget that you have to subtract, or in this case, add it back of the extra subtraction that you have done that is redundant, that not redundant, that is too much, that you actually have to add them back. Okay, so that's the property of joint CDF. In particular, we focus on how to get the marginal CDF from the joint CDF, and then hopefully this generic examples that we're showing over here make sense to you.